Hi everyone, welcome back to our course Manufacturing Process. Today we are going to discuss about bulk deformation process. In bulk deformation, we are going to discuss the fundamental principles of metal forming. So today we are going to discuss material behavior in metal forming, temperature in metal forming, and strain rate sensitivity. So I have already explained about the average stress required to deform a material or a product, that is equal to K times epsilon raised to n over 1 plus n. K is the strength coefficient and epsilon is the maximum strain. And using this, we can find how much is the flow stress required to produce a plastic deformation in a material. Now we have for K and N in the flow curve depend on the temperature. Both K is the strength coefficient and N is the strain hardening coefficient. Both are reduced at high temperatures. So the effect of temperature, clearly it shows that K constant, K and N, strength coefficient K and strain hardening coefficient N, get reduced at higher temperatures. That means at higher temperature, when K and N get reduced, you need a less flow stress to produce plastic deformation in the material. In addition to that, at higher temperature, what happens is whenever we increase the temperature, ductility increases. That means easily we can produce deformation in the material. So this is the effect of temperature in metal forming. As temperature is increased, K and N increases, K and N decreases as temperature is increased. When K and N decreases, the flow stress decreases. As flow stress decreases, less stress is required for plastic deformation. And also ductility increases at higher temperature. This increased ductility at higher temperature will have an effect on deformation, plastic deformation. That means it will be easy for materials to deform at higher temperatures. Any deformation operation can be accomplished with lower forces and power at elevated temperature. So depending on the temperature, we can classify the processes as cold working, warm working, and hot working. These are the three working methods: cold working, warm working, and hot working. Cold working means cold working process is performed at room temperature or slightly above room temperature. Many cold forming processes are important mass production operations. Minimum or no machining usually required. These operations are near or net shape or net shape processes. Advantages of cold forming are better accuracy, closer finishing, etc. Better surface finish, that is the advantage of cold forming. Strain hardening increases strength and hardness. Grain flow during deformation can cause desirable directional properties. No heating of work required. These are all the advantages of cold working. So disadvantages of cold working also there. Before going to disadvantages, let us see what is a cold working process. This is a rolling process. Cold working, we feed material into the roll in between the rolls at normal or room temperature or slightly above the room temperature. The grains will get distorted or elongated. There will not be any new grain formation in the material, but the grains will get distorted and elongated while doing cold working. Large force need to be applied because it is this process is done at room temperature, hence large force or stress is required for the deformation. Surface finishing and accuracy will be quite good comparing with the hot or warm working process, because we do the process at room temperature, hence controlling the accuracy, getting a net shape or near net shape will be possible using cold working. So the grains of the cold working process, as you could see here, the grains will get distorted or elongated in such cases in here. So as I explained here, better accuracy and close tolerance, better finishing, and strain hardening increases strength and hardness. The strength will be more in cold forming comparing with a hot forming process. And then what are the disadvantages? The disadvantages are you need to apply high force or power required for deformation because it is done at room temperature. Surface for starting workpiece must be free of scale and dirt. Ductility and strain hardening limit the amount of foaming that can be done. There is a limit in the strain hardening, how much limit deformation can be possible, because we do the deformation, we produce deformation at room temperature or slightly above the room temperature. Hence, how much deformation is possible, this is another concern in cold forming. In some cases metal must be annealed to allow further deformation. In other cases metal is simply not ductile enough to be cold work. In some cases you have to heat it to produce further deformation. In other cases metal is simply not ductile enough to be cold worked. So this is all about cold working. Now we come to warm working performed at a temperature above room temperature but below the recrystallization temperature. Dividing line between cold working and warm working often expressed in terms of melting point. Melting point is Tm. Then 0.3 m, up to 0.3 m we could say that this is a warm working process. Advantages again, lower forces and power than cold working. More intricate shapes can be possible. Need an annealing to reduce or eliminate it. Here, comparing with cold working, annealing process can be eliminated in using warm working process. So hot working deformation, now we have a hot working process, deformation at temperature above recrystallization temperature. Recrystallization temperature is about 1/2 of the melting point on absolute scale. Hot working usually performs somewhat above 0.5 Tm. Tm is the melting point temperature. If the temperature is increased above 0.5 melting temperature, then it becomes hot working. Metal continues to soften as temperature increases above 0.5 Tm. So enhancing advantage of hot working is above this level. So hot working, as you could see here, the new grains will be produced and internal stresses will be released in hot working process. Cracks and porosity will be relieved, and these are some of the advantages of hot working. So capability of substantial plastic deformation. Another important advantage of hot working is large amount of deformation is possible because we are heating the material at higher temperature, and large deformation is possible because ductility increases and less force required to produce large deformation, etc. Capability of substantial plastic deformation is one of the advantage. Strength coefficient K will be less at room temperature, less than room temperature. Whenever we heat it at high temperature, K reduces. Strain hardening N also reduces on and approximately becomes 0. Ductility significantly increased. So as K and N decreases, the flow stress required decreases, the load force required for working decreases, and then ductility increases at high temperature. That's why sometimes we go for hot working process. Advantages of hot working are work shape can be significantly altered, work part shape can be significantly changed, significant or massive deformation is possible, less force is required. Less force and power means K and N less, hence flow stress less, so less force and power required. Metal that usually fracture in cold working can be hot formed. Some metals cannot be cannot we cannot go for cold working. Those metals can be hot formed. Strength properties of product are generally isotropic. That means it will produce homogeneous structure, so isotropic properties will be produced. No strengthening of part occurs from work hardening. Advantages in cases when part is to be subsequently processed by cold forming. Disadvantages of hot working are lower dimensional accuracy because we are heating the material, and after that we are deforming the material. So there will be because of the temperature change, there will be a lower dimensional accuracy and higher total energy required due to we are heating the material, so total energy required will be more. We supply heat energy. Work surface oxidation, so oxidation is another concern. At higher temperature, production of oxides will be there. Surface finish will be less accuracy, shorter tool life because of higher temperature. Theoretically, a metal in hot working behaves like a perfectly plastic material with strain exponent n is equal to 0. So we have a parameter called a strain rate sensitivity. What is the meaning of a strain rate sensitivity? The metal should continue to flow at the same flow stress once that stress is reached. If you see here, strain rate means it is the speed at which the metal get deformed. The strain rate means the speed or velocity at which the metal or material get deformed. How to calculate strain rate is volume divided by height. Volume is the speed and height is the instantaneous height of the workpiece being deformed. How do we evaluate strain rate? In most practical operations, evaluation of strain rate is complicated because of its geometry, because the strain rate in different regions, it will be different. So strain rate even can reach 1,000 per second or more for some metal forming operations. Effect of strain rate on flow stress. As you can see here, flow stress is a function of temperature. At hot working temperature, flow stress also depends on strain rate. As strain rate increases, resistance to deformation increases. This is known as strain rate sensitivity. This can be explained with the help of a diagram here. As you could see here, as flow stress increases, as strain rate increases, as you increase the strain rate, flow stress for the deformation also increases. Corresponding to corresponding to unit strain rate, we have a value of flow stress that is defined as C. So C is called the strength constant corresponding to unit strain rate for a material. So C is the strength constant, which is the flow stress required to produce unit strain rate. So as strain rate increases, the speed at which the deformation of a material takes place, that is strain rate. As strain rate increases, that definitely we need to supply more flow stress for this. Now you can see here the equation can be written as flow stress is equal to C times epsilon raised to m. Here, as I explained before here, epsilon dot is the strain rate. So epsilon is the strain rate and m is the strain rate sensitivity exponent. So when we represent this graph in a logarithmic scale, we'll get a straight line, and slope of the straight line is represented as em, which is the strain rate sensitivity. Now, effect of temperature on flow stress, you could see here from room temperature to a higher degree, like 1200 degrees Celsius. As we keep on increasing the room temperature, as you could see here, less stress is required for deformation. So less amount of stress is required whenever we move from room temperature to a higher temperature. The plastic deformation will be very easy. That means less stress, less force required at higher temperature. But what happens what happens to the strain rate at higher temperature? If you take 1200 degree, this is the line for 1200 degree. As the strain rate increases, you can see here the more flow stress is required. As you increase the strain rate, you need to have more flow stress to produce the deformation. So as strain rate or the speed at which strain takes place, you need to have more stress or flow stress required for the deformation. So you could see here. So this is the effect of strain rate in the flow stress. If you take 800 degree, you need to have if you want to increase the strain rate, definitely more flow stress is required. Now, effect of temperature on flow stress, as you could see here, at higher temperature, you need a less stress to deform. So this is the effect. As indicated by the graph, you can see here the value of C, unit strain rate, the flow stress. If you take for unit strain rate, that means corresponding to strain rate 1, what is the flow stress? What is the value of C for 1200 degree, 800 degree, 400 degree, etc. You could see here as temperature increases, value of C decreases. So, and the EM, the slope of each part, you can see here as temperature is increased, M, as temperature is increased, you can see here as temperature increases, the value M increases. So these are some of the factors affecting the flow stress and the effect of temperature on flow stress. So increasing the temperature decreases C and increases M, and room temperature effective strain rate is almost negligible. Flow curve is good representation of material behavior. As I explained before, as we increase the temperature, strain rate becomes increasingly important in determining the flow stress. Now, friction in metal forming. In most metal forming processes, friction is undesirable as friction retards the flow. Metal flow is retarded. Forces and power are increased due to friction. Wear of the tool will be more. So friction and tool wear are more severe in hot condition in comparison with in cold conditions. Lubrications are required to reduce friction. Metalworking lubricants are applied to tool work interface in many forming operations to reduce harmful effects of friction. Benefits of lubrications are reduced ticking, forces, power, tool wear, etc. Better finishing, remove heat from the tooling. Now we have a solved example here. The strength coefficient K is given, strain hardening exponent N is given. During a forming operation, the final strain that the metal experiences is 0.85. That means we have the final strain given. The value strain epsilon is given. Determine the flow stress instantaneous and average. We have to find two parameters, instantaneous flow stress and average flow stress. Instantaneous flow stress is equal to that is YF, which is equal to K epsilon raised to N. K is given as 550, epsilon is given as 0.85 and N is 0.22. We get instantaneous flow stress at this parameter, and we can calculate average flow stress, which is YF is equal to K epsilon raised to N over 1 plus N. When we apply it, we get 435 megapascal. Thank you for listening this, and we have one more example here. You can see here a work part with strain height H 100 mm is compressed to a final height of 50 millimeter. So we have a work part, the height or initial height of the work part is 100 mm and final height, it is reduced to 50 mm. During the deformation, the speed of deformation velocity speed is given 200 millimeter per second. Determine the strain rate. Strain rate, that is epsilon dot, that is H is equal to 100, height initial, height becomes 75 and height becomes 51. You could see here strain rate is equal to velocity divided by height. Velocity is 200 divided by height is 100. So corresponding to 100 mm, velocity by 100, that is 2 per second. Then second part, determine the strain rate at a height 75 mm. So velocity by height 75, you will get strain rate at 75. Similarly, strain rate at 51 can also be calculated from these equations. Thank you very much for listening. Thank you.